Hello everyone, I just want to go over some aspects of homework 5. So to start off with, I want to go over a little bit of problem 2. And most people, everyone got the induction correct, but really the proof's largely not complete when the order of the multi-index is 1, and you really have to use dominated convergence theorem to differentiate the Fourier transform, as we'll see in a second. So I just want to go over these details. I think they're not trivial, not super deep, particularly with Schwartz functions. Anyway, so all right, so so the Fourier transform, course, is f of u e to the minus 2 pi I x dot u du. So when alpha has order 1, this is just partial derivative. Say with respect to xj, doesn't really matter what j is. All right, so just usual partial derivative definition. So let's say EJ is just the jth unit vector. So J 0, well, everything is 0 except in the jth spot. All right, so so this is just definition of partial derivative. All right, so let's evaluate this limit here. At least again to do that. Okay, so yeah, if you combine everything into one integral, f of u e to the minus 2 pi I x plus h ej, and h is just, well, just regular calc 1 limit. H is just a real number going to 0. Okay, so minus e to the minus 2 pi I x dot u for h u. Whoops, sorry about that. All right, so just factor, we'll distribute the x and the h ej. H ej dot u just gives you h times the jth component of u, which I'll call uj. So this is going to be the following. I'm going to factor out an e to the minus 2 pi I x dot u. So I just get e to the minus 2 pi I h times uj. And again, uj is the jth component of u minus 1 all over h. Okay, and so to justify dominated convergence theorem, we need a dominator independent of h. If you want to be precise, you can pick a sequence hn or hk. I guess we have n already here. Hk going to 0, but anyway. And this is a u, sorry about that. It looks a little weird, but okay, so for getting a dominator, we just smash in absolute values. So absolute value of this here is just 1, e to the minus 2 pi I x dot u. X and u are real, so this just equals to 1. So it's absolute value of f of u times absolute value of this whole thing here. And by mean value theorem, we'll get this is bounded by 2 pi times the absolute value of uj. And absolute value, uj f of u is certainly an L1 because f is a Schwartz function. So no problem there. So I'll just do the mean value theorem real quick. So make life a little easier, let's call this star here. Okay, so we want to estimate this. So star here, I'll put absolute values in a second. Well, just write this in terms of sines and cosines. So, oops. So it's cosine 2 pi h u j minus 1 over h plus I sine 2 pi h u j over h. All right, so we're going to use mean value theorem with respect to two functions. I don't know, I'll say g and h. G, maybe h is a bad. Let's do little g and big G, I don't know, whatever. So here my function is just going to be cosine 2 pi h u j because, well, g of 0, this is g of 0 over h. And here, well, basically the same thing. Sorry, not u, but h. Yeah, so it's going to be sine 2 pi h u j. Okay, so by the mean value theorem, this is going to be, well, it's h minus 0 over h. So the h's cancel out times, well, the derivative, which is 2 pi uj. Uj is a constant. It's minus, I guess. And, sorry, this was a minus here, but cosine is even, so cosine minus 2 pi h u j is without, the same thing as without the minus. And really, it should be a minus here. That matters much because sine is odd, so pull out the minus. Get a minus here. The derivative of cosine is sine. So it's sine 2 pi h star j for h star between 0 and h. I mean, this has modulus 1, so it doesn't matter. And it's going to be minus I 2 pi uj cosine 2 pi h star star uj for h star star between 0 and h here. Okay. Again, this is really g of h minus g of 0 over h, so right. G prime is 2 pi uj cosine 2 pi h uj. Okay, so absolute value is going to be, well, this is actually just going to be, or rather less than or equal to, because both of these have modulus 1, or modulus less than or equal to, or absolute value less than or equal to 1, 2 pi uj. is just 2 pi times uj, an absolute value. Okay, right, so that gives us a denominator. So we can actually pull this limit inside. So let's do that. Or rather, I'll go to the next page here. So I dominate convergence theorem. This derivative here equals. So, I mean, I'm basically doing what people did, which is pull derivatives inside the integral, but you really have to justify that. So it's f of u, e to the minus 2 pi I x dot u. There's this limit here. E to the minus 2 pi I h uj minus 1 over h du. And you do this limit. This is, well, either L'Hopital's rule or just differentiate here. I don't know, use big F. My function here is really big F of h is e to the minus 2 pi I h j. So you're just differentiating f with respect to h, then plug in h is 0. So you get a minus 2 pi I uj. Minus 2 pi I j. E to the minus 2 pi I x dot u. Yeah, and uj, f of u is in L1, so it's perfectly well defined Fourier transform. So it's minus 2 pi I uj f. This Fourier transform with x. Okay, and the problem, well, number 4 is similar in that most people did this right, but you really should have justified interchanging the sum and the integral. So for number 4, what do I mean by that? Well, so remember how to do number 4. You just simply write Pf of z is going to be the sum here, just the definition. Z to the k. So it's going to be 0 to 1, f of t, e to the minus 2 pi I kt dt times z to the k, and you combine the exponents, so it's integral 0 to 1, bring everything inside, z e to the minus 2 pi I t whole thing to the k dt. Okay, now, right, so if we can get a bound independent of k, we can use the dominated convergence theorem and interchange the sum and the integral. So in particular, let's just get an estimate for the L1 norm of this integrand here. So 0 to 1, f of t. So yeah, let's actually sum this up. K equals 0 to infinity, f of t, e to the minus 2 pi I t z. the k dt. Well, that's less than or equal to 0 to 1. Right, so f of t. Now, for non-negative functions, you can willy-nilly interchange sums and integrals, no problem. Just monotone convergence theorem. So z to the k. Pull this out. So this is just going to be less than or equal to 1 over 1 minus modulus z times the LP norm of f. And in particular, for fixed z, this is finite. So, right, so I can interchange dominated convergence theorem, sums, and integrals. So just do exactly that. So this is going to be the integral f of t, k equals 0 to infinity, e to the minus 2, or rather z in front, minus 2 pi I t k dt. And this is just geometric series. Obviously convergent geometric series, because in modulus, this whole thing is modulus z, k, z is in the unit disk. So this is f of t over 1 minus z e to the minus 2 pi I t dt, which is exactly what the problem has. So again, nothing too deep justifying interchanging sums and integrals, but you really need to do that, particularly when you write a thesis and analysis. If you do, you know, someone asks, well, how do you justify this? You really need to be able to answer that. So anyway. I remember what the problem is. So everyone got this part right. Or rather, everyone got that if C is bounded, then at the very, or rather, everyone got that at the very least, the norm of R right here less than or equal to 1/2 1 plus the norm of C. So I'm not going to repeat that. Really, just add. Not much to that. Okay, so right. So let's assume R is bounded. Okay, so let's go to the whiteboard here. So let's say F is an S. So F is going to be this finite sum, I don't know, minus n to n. Well, let's write it in terms of Fourier series, f hat of k, e to the 2 pi I k t. So that's what f of t is. Okay, right, so right, so what's PF? Let's just go back a second. PF is this here, so we just plug in and see what PF is. Right. So in this case, well, we cut off everything negative. But you can think the Fourier coefficient is clearly 0 when k is larger than n. So you go from k equals 0 to n. f hat of k z to the k. All right, so we can, by definition, and people, when they did the HP norm, they were, instead of had lim sup, they had sup, which is correct, but it's not trivial at all to prove that actually as a function of r, this is increasing, which is why I put a lim sup. And I want to kind of emphasize that the Hardy space norm is basically kind of like a unit circle norm, where it's not clear at all that that's the case if you just take the sup over all r. Again, it's not clear at all unless you prove that it's increasing with respect to r, which you do, and Professor Zhu probably proved that, but anyway. So this is going to be lim sup 0 to 1 times the sum here, k equals 0 to n f hat of k r to k e to the, we'll just write z. Well, it's you plug in, the definition that I gave is plug in r e to the 2 pi I t. So let's just do that. Right. Right, the definition, go back real quick. Right, so you just, whatever f is, you plug in r e to the 2 pi I t, integrate modulus raised to the p, take the lim sup. All right, so I'm just plugging in, plugging in r e to the 2 pi I t for z. And, right, so the idea here is you can use dominated convergence theorem. I mean, forget about a sup here, this limit exists. And the key here is you have a finite n here. So, I mean, you can just smash in absolute values. R is between 0 and 1, so it's an absolute value is bounded by 1. Absolute value of this whole thing is 1. Absolute value of the Fourier coefficients certainly bounded, because f is in LP, so it's certainly an L1 on 0 to 1. So at most, the bound is n, or n plus 1, times the L1 norm, or rather the LP norm of f. Okay, so there's no claims of bounds independent of n, but that's all right. But the point of doing this for f in this s here, where s is just the span of these exponentials, is that you can trivially invoke the dominated convergence theorem and interchange this limit and integral. And again, lim sup is a limit if the limit exists. Okay. So this equals dominated convergence theorem. Whoops. This limit here, again, it's really a limit. And there's also no, right, there's no issue with handling this limit here. This is just a limit of a finite sum. R to the k e to the 2 pi I k t dt. Right, this is a finite sum. So this is certainly continuous. There's just no issue whatsoever. You know, yeah, there's just no issue at all. So some people did things like the HP norm is the little LP norm of F hat. That didn't make any sense, to be honest. It's, you know, even comparing the LP norm to F and the LP norm of the Fourier series, that's very subtle unless P equals 2. P equals 2, the L2 norm is the little L2 norm of Fourier coefficients. But when P is not equal to 2, that's very subtle. And if you're curious about that, there are connections. It's called Littlewood Paley theory. Something we would do if we had more time. But anyway, there's really, yeah, you can't compare the Hardy space norm or the LP space norm of anything to just Fourier coefficients necessarily. Right, so, so anyway, because this is nice continuous function with respect to R, there's no issues here. It's a finite sum. This is just 0 to 1, just R equals 1. K equals 0 to N. F hat of K. E to 2 pi I K T. And lo and behold, this is just what F is. Or rather, this is what RF is. And this is going to be 1/2 1 plus the norm of C, S2 P 0 1 times the LP norm 0 to 1 of F. So remember what R is. R takes any function and just cuts off the Fourier series. This throws out the negative terms for the Fourier series. So you do that for this function here, F. And we get K equals 0 to N. It's exactly what we have here. And right. Right, and you know, just from what everyone did correctly, this part here, remember we have this bound here. Okay, well, sorry, so we assume F is 1. So back here, this here. If the norm of F. Okay, right, so, all right, so what does this actually mean? Right, so if we have, let's say F in LP 0 to 1, Fn in S, Fn converges to F in LP, well then we know from what we just proved that, yeah, and I should also just really quickly mention, let's go back a second, that this is definitely holomorphic. I mean, it's a finite sum of holomorphic functions, so there's no issues whatsoever about this being holomorphic. Okay, so the HP norm, well, P is definitely linear. So I guess really we actually don't necessarily want the LP norm to be 1. We actually do get LP norm here. Oops. Like that. Okay, so this is in S. S is definitely a vector space. So this is less than or equal to this constant here, 1/2, 1 plus the norm of this conjugate function. Let's call that C. So it's Fn minus Fm LP. Okay, so in other words, assuming, well, not assuming anything, this is Cauchy in the Hardy space. So assuming it's complete, this converges to, I don't know what, something, let's call it F, in HP. Okay. Right, so thus this HP norm here of big F is just this limit here. So we're almost done, not quite. Right, this is less than or equal to the C. Again, because Fn is an S, LP, well, Fn converges to F and LP. So this is just C, LP. And again, C is just this, this is what C is. So I'll do this in blue. Maybe I'll make this capital C here for the conjugate function. Yeah, this is what my C is, 1/2, 1 plus the norm of this conjugate function operator. All right. Yeah. Okay. So we're still not quite done. The only thing to do is, well, we still don't know. So put a, well, maybe I'll do this in, I don't know, do the red here. Yeah, we just don't know. We don't know if this is PF. We just don't. I'm sorry, this should be HP on top. So we've proven that certainly the this projection operator P extends from S to the Hardy space, but we don't know if this extension is actually PF. So let's prove that. So the answer is yes here. Actually, PF is big F. So to finish up, I claim that PF equals F pointwise on the unit disk. So they are literally the same function. Okay. Right. So yeah, and I admit this is a tricky problem, but might as well give at least a few challenging problems here and there. Okay, so let's prove this. So first I claim that pointwise PFN equals PF. Okay, so from problem 4, so for fixed z, we know that this is going to be this integral here, Fn of t, 1 minus z e to the minus 2 pi I t dt. Okay, well, so maybe it's a little easier to do this here, actually. Pf n of z minus Pf z. Okay, so well, P is linear, so f of t. And there's really not a whole lot of subtlety here. Just use Holder's inequality. Forgot the limit. Sorry about that. So Fn minus f times the LP norm of 1 over 1 minus z e to the minus 2 pi I t dt. Okay, and we're not claiming any uniformity in z. We'd be in big trouble if we were. We're not doing any Hardy space norms. Just z is fixed. It's in the unit disk. So this whole thing here, by the reverse triangle inequality, is less than or equal to 1 over 1 minus modulus z to the p. Integrate that from 0 to 1. So it's finite, this blue bit. And we know Fn converges F, so this is 0. So yeah, we're definitely in trouble if we do anything z goes to the boundary. We're not. We're just saying for fixed z, we have Pfn converges to Pf. Pointwise on the unit disk. Okay, and last but not least, I want to finish this up by claiming that I'll write it like this, that Pfn converges pointwise to big F on the unit disk. So in other words, that'll say f of z for each fixed z is this limit here. Well, we already computed this limit. It's Pf of z for any z in the disk. Yeah, so we'll have Pf of z is f of z in the unit disk, and that's exactly what, so maybe pointwise, I just mean for each z, Pf of z equals f of z. Oops, don't want to stamp anything. All right. Yeah, this is a little tricky, but so let's use the Cauchy integral formula on the circle of radius r for r between 0 and 1. Okay, so Pfn of z. So F is holomorphic because we're assuming the Hardy space is complete. Pfn is Cauchy in the Hardy space, so we're assuming it converges to F, some F, big F in the Hardy space, which implies that it's holomorphic. Pfn, we mentioned, is certainly holomorphic. So this equals, for any r between 0 and 1 over 2 pi I. Let's integrate u equals r, Pf n of u, f of u, over u minus z du. Now this is true for any r whatsoever, so I can let r go to 1. And I should mention I use lim sup instead of lim because it's the limit will exist, but that's not trivial at all. So there's a lot of beautiful depth in the Hardy space. Yeah, it's not trivial at all that actually the limit. Well, I mean, I guess it is. I guess like I said, it's not trivial that the limit. It's increasing as of this. Forget about lim anything. This is an increasing function of r as r goes from 0 to 1. That's not trivial at all. So the limit exists. And given something in f and HP, it's not trivial at all that you have convergence as r goes to 1 to a function on the circle. Anyway, it's getting into some, non-trivial Hardy space theory. Don't want to go there. Okay, so what we're going to do is just parametrize. Just parametrize this. U is re to the 2 pi I t. Du is 2 pi I. Yeah, it is 2 pi I. Excuse me. Re to 2 pi I t dt. All right, so again, I'm going to estimate the bottom. Well, I'll just plug everything in. So yeah, I do get an r here, which who really cares? R is going to 1, but whatever. Okay, so this is actually fairly reminiscent of this Hardy space norm after I use Holder's inequality second. So it's Pfn, u is r e to the 2 pi I t minus f r e to the 2 pi I t. Sorry about that. Over u minus z. Whoops, don't want that yet. Okay, well, I can just throw in absolute values. Now things are not very subtle, so less than or equal to, just smash in absolute value here, absolute value here. Okay? And again, this denominator here is, well, it's just going to be, R is going to 1, Z is fixed. So this is bounded by, well, this whole, yeah, so I'll write kind of in red here. I'll erase it in a second. So yeah, just use reverse triangle inequality. It's 1 minus, or I guess it's R minus modulus Z here. Yeah, so yeah, just reverse triangle inequality. So this is going to be less than or equal to, well, take the LP norm of the top. That is my definition of the Hardy space norm. Okay. So this is PFN. So this is basically a proof that point evaluation is bounded on the Hardy space. Yeah, and hence Hardy space is a reproducing kernel Hilbert space. Anyway, so embedded in this homework is actually quite a bit of the basic function theory and Hilbert space theory of the Hardy space. But anyway, right, and we get in the denominator 1 minus modulus Z. Okay. Whoops. Right, so, so for fixed Z, this limit here, and fixed Z is all we get, and that's all we, bond. Point-wise, we get this here. Okay, so yeah, that was a lot, but anyway. So yeah, hopefully this was interesting, useful, helpful. If you're enticed by the connections between holomorphic function spaces and harmonic analysis this course, there is a very classic book. It's a very challenging book, I'm not going to lie. It's, it has a reputation for being extremely challenging, but it's called Bounded Analytic. That's such an innocent little name. Bounded Analytic Functions by John Garnett. Yeah, very, very deep, interesting book that really connects a lot of kind of this kind of harmonic analysis, Fourier analysis, kind of estimates type of thinking throughout this course, and holomorphic function spaces, and particularly bounded analytic functions on the unit disk. Everything's on a unit disk here. But anyway, all right, this is a long video, sorry about that. Hopefully someone finds this useful. So long, take care, it's over, it's finally over. Yep, until the winter, until February. Take care, enjoy your break. I know I will get a lot of research done, and anyway, bye-bye. Stay safe, bye-bye.